go.
We are now pleased to welcome Dr. Bob Mumgaard, CEO of Commonwealth Fusion Systems, and Tom Gibbs, Senior Business Development Manager at NVIDIA, for a fireside chat with Martijn Rasser, Senior Advisor for Economy at SCSP.
All right. Good morning, everyone. Thank you so much for being here. Bob, Tom, welcome.
Thank you. Happy to be here.
So the title of this session is AI for Fusion, Fusion for AI. I think that really captures that symbiotic relationship between fusion and AI that the Commission's report highlights. So to kick things off, could you tell us, what the history of collaboration between CFS and NVIDIA, how that's been working, and what we can expect? So maybe start with you, Bob.
Yeah, so you think about AI, what people don't usually know is that there's actually a large set of people in the AI community who have fusion backgrounds. That fusion over the years has produced large data sets, very complex physics, also produced PhDs that didn't have an industry to go to, and many of them ended up in the AI machine learning space. So there's been this long history of collaboration between the two areas, just generally. At Commonwealth and similar to other companies and labs, we have very complicated workflows to be able to understand what's going on inside the plasmas, to be able to model it faster. And so those workflows rely on equipment from NVIDIA. Spark, our facility in Massachusetts, actually is wired as a data center in many ways. And so we started to talk to NVIDIA about how could we accelerate things? How could we go faster on the types of compute that we were doing? How could we start to think about what to do with the data from Spark, how to best get that into the models that would enable future designs. And really over this, it wasn't that long ago, but over the summer it got formalized into actually working groups that were embedded with each other to look at digital twins and how to use the AI workflows to accelerate the work that we were doing in a more conventional way.
Yeah, Tom?
Sure, and I think in some ways we've been working with Commonwealth Fusion and the problem set for a decade or more. As part of the Exascale program with DOE, we started to engage with some of the key simulation codes. So Princeton Plasma Physics Lab, MIT, basically some of the pedigree of the folks that are at Commonwealth, we've been working with them now for years. AI has really opened the door to being able to both design, operate, and maintain and realize commercially viable fusion. I think it's important when we're thinking about AI, I think there's really two types. One, I think people are aware of, like ChatGPT. So that would be like an agent to do autonomous operation of the controller to help the designers. The other, and I think this is really where I've seen the biggest bang for the buck, so to speak, is taking some of these expensive simulation codes, using those to train an AI model, and then the inference runs thousands of times faster. And what we're just beginning to be able to do, and we'll be demonstrating, I'll give you a sneak peek, GTC DC in a couple of weeks, we'll be able to show you some of these surrogate models running in real time. And we're using that to help enable and jumpstart the work that we've been doing with your team. So really in 6 months, because of some of the head start we had, we've been able to get the early parts of a digital twin for Spark already integrated into our Omniverse toolset.
There was some interesting news out of MIT recently, a prediction model all about how plasma behaves during a ramp down. Bob, could you talk about how you're leveraging AI and advanced simulation to solve some of the very difficult engineering challenges associated with building a tokamak and really bringing it to commercialization?
So inside a fusion power plant, at the heart of it is a plasma. They all have at the heart of it plasma. And that is a system that is very nonlinear, which means it's very complicated, right? It dances, it does things, it goes unstable. And in some ways, it's beautiful. It's like why we look at the Northern Lights, right? But to harness it and get the most out of it, you have to understand it. And to understand that, to do it in a brute force way requires the largest computers that have ever been built. And in fact, some of the largest conventional simulations ever run on, say, a DOE supercomputer for civilians have been to understand the plasmas inside machines in national labs and universities. So you cannot use that as a design tool. It's too cumbersome. You can't say, hey, I have these 7 different designs, which one's best? Go compute it and come back a year later for 1 computer cycle to finish. But what you can do is use AI models to drastically accelerate that compute. So to train models so that you can actually ask the model, hey, like, of these 7 different designs, which one's the best? You can get that answer much faster. You get that answer fast enough to actually today put it in a design cycle, meaning someone goes and talks to their colleagues and thinks about it. But we can see that you can actually get it fast enough to put it into a control cycle, meaning the software in the plant is doing that in near real time. And so that's a huge accelerant. And it's an accelerant for all the different types of fusion concepts, because it's all plasma physics. And so we're starting to see that happen, of us translate these models from big brute force, big iron, into surrogate models, which do the same basic output, maybe not as high fidelity, but much, much faster. And so that is helping on design, it's helping on control, it's helping people come up with novel configurations altogether. And we're still early days at this, so this is something that we think will accelerate. And the more data we get from experiments that are in the right regimes, things like Spark, but also other existing ones, the better and better those models will get. And the better and better the models get, the faster they go, and the faster they go, the more we can use them. And it's really a virtuous feedback loop.
Yeah, it's an absolutely fascinating development. It's something I think that, yeah, I hope people pay attention to, right? Because it seems like it's really pushing the boundaries of what's possible now. So Tom, NVIDIA is at the center of revolution in AI. It's very energy intensive. And Bob, the Commission's report specifically cited fusion as a source of geographically unconstrained power, and that you can have co-located data sources for these fusion plants and data centers. So how does your partnership lay the groundwork for a future where fusion plants are built specifically to power the next generation of AI?
Well, what I've experienced in working with Commonwealth, I think, has been, a manifestation of the public-private partnership benefits, that they have a real problem. You're trying to build Spark. So they can define a workflow and give us targets. This is a problem, and the one we're looking at now is how much heat is generated from the plasma at the first wall of the tokamak. This has been a theoretical problem that people have looked at for a long time. And so we're working with your workflow and getting the key codes in that workflow to be accelerated, and then building the AI surrogates. To put it in perspective, one of the codes that's used in your workflow takes anywhere from 2 to 3 weeks to converge for one instance. So imagine trying to use that in a design workflow. Well, it turns out that the neural net that we can train is 1,000 times faster. So you can actually now begin to, as we build this workflow with your team, we can see that we can get this done in a design cycle, and we can start to see that we can build the first wall of the plasma of the reactor and get this to market faster. And then how these get deployed, the world is your oyster, I think.
Anything you want to add to that, Bob?
Yeah, we're just scratching the surface, right? Like, in the future, the AI enabling fusion, fusion enabling AI will just get tighter and tighter, because they're both based on how do you tame complexity, how do you get the most out of a system, and they both have similar mindsets in there of hypothesis testing, design loops. Whenever we put the teams together, the teams they think the same way. And so I think we're at the beginning of this, and it's very exciting to think where we'll go. Ultimately, of course, to power AI in the future, we're going to need a lot more energy, right? But the fact that we're actually getting fusion going faster gives us a better shot at that. So it's very synergistic.
Yeah. So the Commission report frames fusion as a race for technological leadership. Several of the speakers this morning have said the same thing. So how does a deep collaboration between a leading US fusion company, between a foundational US technology company like NVIDIA, how does that position the United States for success? How does that accelerate that technological race in a way that's favorable to the United States?
I think it was mentioned by Chris in his opening talk today that the one thing that the U.S. has that nobody else has is the commercial ecosystem, of which Commonwealth is a clear example. And I go back to kind of my beginning in supercomputing. That's what we called it back in the 80s during the Cold War. And there, I think, again, you had startups and that commercial community, the innovation, the speed with which they work, and the fact that they define the problem and then go solve it. And my experience then actually was with an entity you may know of, the Lockheed Skunk Works. And to me, working with Commonwealth Fusion brings me back to those days. They work, they're innovative, they get stuff done, and they do it fast. And that gives us something to go, we can go chase them and work with them, and it's really exciting.
I think on the other side of it too is like, Fusion is it's like an apex predator of technology. You need to have this big ecosystem of all these other technologies in order to make it work, right? And if you don't have that ecosystem, you just won't get Fusion, right? So like in this ecosystem, you need to have the best people in the world at building simulation tools that like are from Maxwell's equations and Einstein's E equals mc squared, right? You need to have that. The DOE has that. The labs have that. You need to have suppliers that can build complicated things, forgings and big pieces of equipment. You need to be able to make these things at high precision. You need to be able to make them, in a fast cycle. The U.S. actually has a pretty good cycle, pretty good community of that. It's not, you don't need it at extraordinarily high volume. You don't need it at like really low commodity costs, but you need it right. The U.S. has that. And then you need to be able to have the ability to take complicated plasma physics and trim it down to something that is manageable and put it into a workflow so that a team of people can say, hey, we got to make some design decisions, like how twisty should our accelerator be, or how sheared should our pinch be. Well, that's going to take big compute, and that's where the AI is really, really happening. We have that in this ecosystem. You need to have the ability to construct things, not like mega projects, but like big projects, complicated projects. We have that in the US. So like in Fusion, we're seeing these things layer on top of each other that really do benefit the US somewhat uniquely, that if you take any one of those pieces out, like you get a much worse Fusion ecosystem. And adversaries are missing some of those pieces. And so that gives us, I think, in the US, a current leg up. There's other things we need to do as well. Like we actually have to have test stands to be able to test things. Well, that's the role of government, and the report calls out, we need to build that. That's a currently missing piece in the ecosystem. We currently don't know how the first power plants will get financed and get to the grid. We've got to put that in place. That's a missing piece. But the fortunate part is that like the really cutting edge things, like those are the strengths of the US. And those are the hardest things to build. Those are take the longest time. And we're seeing them start to build really strong cross-linking, and this is a great example, but there's others, at those really, really, really cutting-edge pieces. And everything else, I think we'll be able to figure out.
We didn't mention the university part of the ecosystem, and I think that's another thing the U.S. has. Our university ecosystem is really, I think, second to none. And the ability to really bring, the Department of Energy, the national labs, the commercial ecosystem, and our university ecosystem together. And we see this when we're working on the workflows, because as AI is evolving, and I've never seen anything like this. I mean, the state of the art with AI models changes every 18 months. So the university ecosystem is on top of that. So when we're building the AI models for Commonwealth, we'll be bringing the university folks in to be looking about the AI models to see if there isn't a new one that can do the same AI with less infrastructure. And I think, again, that gives us a leg up.
Well, it's encouraging to hear that you both see America's traditional strengths, that dynamism, still being very much at the forefront of these breakthroughs. So that's very encouraging, of course, for everyone here in the room. So Tom, I want to talk about data, right? So all these fusion experiments generate petabytes of data. in addition to beyond pure compute, how is NVIDIA helping people process and extract insight from these vast data sets?
Well, what we have been doing a couple of things. One, we have been integrating our GPUs into the real-time control systems at the experiments. So, and that can go, that's bidirectional. So we can use the GPUs both to do disruption and prediction for control, as well as to help filter data as it's coming off the experiment. One thing we are seeing within the experimental community, and one thing I will say, as we engage with the fusion community, we have been reaching out and engaging with General Atomics, folks at UKAEA, folks at EPFL in Europe, so the UK Atomic Energy Authority and the European fusion labs, to do early prototypes of the experimental facilities. And with that, we're finding that they're changing the way they're going about allocating the experiments. In the past, it was kind of siloed one at a time. But now they're thinking about, can we get a continuum of data, because we're going to need that data to train the AI surrogates.
And this is one of those areas where the strength of the fusion community globally is that we've built a lot of experiments that actually are very different from each other. So we have a huge parameter range of things that we've looked at. Historically, those have all been individual labs doing their own experiments, like making a plot. It's like I'm going to have a dependent and independent variable plotted up. Well, what we're seeing now is a movement, and ITER has started this, so this goes back a ways, of saying no, this is all one set. And we have multiple insights built from these large, expensive experiments into what is fusion. How does a plasma work? And so to be able to unify those into a single model, to be able to get the data, all training a single or a set of models that span that whole experiment set. The IAEA has put that as an initiative. ITER is trying to facilitate that. We're a part of that at CFS. And what that'll do is allow us to say, okay, we really understand this at the level that we can base power plants on it, and we can now do experiments at any given place that's going to make the whole better, right? So hey, if we had this one piece of data from Spark, this one piece of data would make this whole model much more accurate in this way. Go get that piece of data. Or it might be that there's an experiment that needs to be run at the Japanese tokamak or the UK tokamak that could actually make this whole model way better, that would make the next generation of fusion power plants better. And that's an open science idea that has been a part of fusion for a very long time, and is a key attribute of being able to accelerate this, where Tom's team isn't just thinking about, okay, what Spark is, but thinking about how can we use the experiments at all these labs to make the model better, so anyone who uses the model has the sum of what we've done.
Yeah, building on what Bob said there, I think going back to the symbiotic relationship of AI and fusion, in the past, there really wasn't that much of a need for the different experimental facilities to cooperate with each other because they were doing individual experiments. But AI is the reason to start to work together, because we want to start to build surrogate models and build control systems. And so each of those experiments can contribute in a way that in the past might not really have mattered. And AI becomes really the reason for this kind of collaboration.
So to close, let's look ahead at milestones. So what breakthrough should we be on the lookout for coming out of your partnership in the next 12 to 18 months?
I'll let Bob start.
Yeah, I think we're working towards a digital twin, which means that you have the most important attributes of the experiment of Spark in this case, captured in a model that can run quickly, so that you can always have a snapshot of what that machine is doing. That's going to take a long time to do, but ideally, if we get that into shape, that could be, we actually can predict what the first spark pulse looks like before we actually do it, and keep up with that prediction while it's running in real time. That it would be a real big achievement to have that level of fidelity distilled down into an experiment. We've never been able to do that on any given fusion experiment to date. But that would be a building block to, it would be a big marker in the use of AI for this.
I'll echo. I think that's a great target to shoot for. And in the near term, Bob, I think what I want to do with your team is get that workflow that's modeling the heat dissipated by the plasma in Spark, get that workflow modeled and integrated into the initial design, computer to design files, so we can demonstrate that next year. That is a near-term milestone I'm hoping we can do probably in the next 6 to 9 months.
Excellent. Bob, Tom, thank you both so much. This was great. Appreciate it.
Thank you.